In this video, we will demonstrate how to calculate root mean square speed of gas particles and how to use them. Now, root mean square speed is just a fancy term for average speed of a collection of gas particles or molecules. So, for example, if you have a gas and you raise its temperature, the average speed of those gas particles is going to increase. And if you maintain a constant temperature, if you compare different gases, then heavier gases will move slower on average than lighter gases. There's actually an equation to calculate the root mean square speed of a gas given its temperature and its mass. Now, as we saw, the average speed of a gas is directly proportional to its temperature, and it's inversely proportional to its weight, or its mass. And in this equation, we see that it is equal to the square root of 3 times the gas constant times the temperature divided by the molecular weight. Now, the root mean square speed is in meters per second, temperature is in Kelvin, but we have a new gas constant here. We're talking about speed. We have to use the gas constant that has the units of joules per Kelvin per mole, not liter atmospheres. And we see that molar mass in this case is not in grams per mole, it is in kilograms per mole. Now, this is a little odd, but we will see why, and we will see how all the units work out in the end. For example, calculate the root mean square speed of nitrogen at 25.0 degrees Celsius. Alright, well, here's our equation. We need to understand that when we're talking about a gas, we're talking about gas in its elemental form. Nitrogen is one of the genuine elements, therefore it is diatomic. We plug in our new gas constant, we convert our temperature to Kelvin, and we need to convert our molar mass into kilograms per mole. Now, as we start canceling out units, we notice that in the end, we are actually left with joules per kilogram. Okay, this is a bit of a problem, and this isn't even our final units. This is the square root of something joules per kilogram. Well, if we recall, 1 joule is defined as 1 kilogram meter squared per second squared. Aha! So, if we take this conversion, we substitute in this kilogram meter squared per second squared in for a joule, these are our new units. Now, kilograms will cancel out. This is the reason for converting molar mass to kilograms per mole. Now we have the square root of meters squared per second squared. So if you take the square root of anything squared, it's just, in this case, meters per second, which is what we wanted in the end. A more useful application of root mean square speed is comparing the speed of two gases based on their molar masses. Now remember, the speed of a particle is inversely proportional to its weight, or its mass. So you notice that the root mean square speed of molecule 1, or particle 1, as compared to the root mean square speed of particle 2, is equal to the square root of the molar mass of particle 2 over that of particle 1. It's inverted, and you have to be very careful that you plug everything into the correct variable when performing this calculation. So for instance, calculate the molar mass of an unknown gas that moves 0.9553 times as fast as HCl at the same temperature. Okay, so what does this mean? We have not actually been given any units for our speed. Well, that's because it doesn't matter. Here we are comparing. We are comparing a ratio. Therefore, the units are all going to cancel out here. And also, what does it mean to move 0.9553 times as fast? Well, again, this is a ratio if we think about this. We are comparing, and arbitrarily we're going to put the unknown on top and the speed of HCl below. What this means is that if HCl is moving at a speed of 1, that means that our unknown gas is moving slower. It's moving at a speed of 0.9553. If our gas was moving at half the speed, then it would be moving at 0.5 times as fast. And if our gas was moving at twice the speed, it'd be moving at 2 times as fast as HCl. Okay, so now we arbitrarily plug in our speed of 0.9553 in the numerator and the speed of HCl in the denominator. And now we have to make sure that we put the molar mass of our comparative gas, our HCl, on top in the square root, and our molar mass of our unknown variable remains down at the bottom. Now all we have to do is solve for the molar mass of the unknown. Now to get rid of that square root, we square both sides, and then we isolate the molar mass of the unknown. And you notice here that we don't have any units to cancel out. In the end, the units that we started with are the units that we get, grams per mole. And this answer makes sense. We need a gas that has a molar mass greater than that of HCl, 36.46. And if our answer turned out to be smaller than 36.46, well then we know we'd made a mistake somewhere. But in this case we didn't. Molar mass is greater at 39.95 grams per mole.